So the last thing we need to explain about the formation of our solar system are the exceptions. A lot of the exceptions, particularly with the planets, can be explained through a giant impact. So something that we see with the Earth is that it has a large moon. It's one of the 7 largest moons in the solar system, and it's the only terrestrial planet to have a moon of such a size. Well, all evidence that we can tell right now from Earth rock, moon rock, and other sources is that the Earth got hit really hard early on. Specifically, there was an impactor, probably about the size of present-day Mercury to present-day Mars, that crashed into the Earth. This led to a whole bunch of debris being ejected, which then reaccreted, forming into the Moon. Similarly, we can use this idea of a large impact to explain Uranus's rotation. So remember, Uranus isn't rotating nice up and down like most of the rest of the planets. It's actually tipped over. If it was hit really hard, then it could be tipped over on its side. As we look at Mercury, Mercury has a surprisingly high density, which suggests that it has a much higher ratio of iron to the other rocks and minerals. Well, one possible explanation is that it got hit really hard, which actually vaporized a lot of the rock. And we've mentioned that Venus spins backwards. It has a retrograde rotation. Well, one possibility is that it formed spinning the direction that we expect and then got hit really hard, so now that it spins backwards. A lot of the times, anytime there's something weird with one of the planets, our go-to explanation really seems to be a giant impact. Now, we've mentioned that some moons have a retrograde orbit. Because of conservation of angular momentum, we'd expect that moons should orbit around the planet in the same direction that the planet is rotating. However, we find that there are some moons that are orbiting backwards. These are the ones with the retrograde orbit. Now, the amount of energy that would be required to cause a moon that was going the right direction to be hit and going backwards would be so much to actually shatter it. So in this case, it's not going to be a large impact. Instead, our best guess, and the evidence points to, that these are actually captured. That these things used to be asteroids or comets that got too close to the planet and got pulled in by the planet's gravity. And because of the way that it got pulled in, it ended up being on a retrograde orbit. Now, another thing that we can ask about the formation of the solar system is, so when did it happen? How old is our solar system? Well, the way that we determine the age of our solar system is through radiometric dating. So the idea of radiometric dating is there are certain isotopes. So an isotope is an atom, but with varying numbers of neutrons. There are certain isotopes which are radioactive. What that means is they spontaneously change from what they are into something else, from one kind of element into another type of element. And during this process, they generally give off harmful radiation. Well, the starting isotope is what we refer to as the parent, and then what it turns into is the daughter isotope. We can quantify how long this process takes by using the half-life. The half-life is the amount of time it takes for half of the material to decay. So when we start out, we have 100% parent isotope, and after one half-life, we have half parent and half daughter. After another half-life, then we're going to have half of the remaining parent. So we end up with half of a half, or after 2 half-lives, we only have 1/4 of the parent isotope. After 3 half-lives, we have half of a half of a half, or 1/8, and so on. So what happens over time is we decrease the amount of parent isotope, but as that happens, we increase the amount of daughter isotope. So what we do to figure out the age using this system is compare the amount of parent isotope to the amount of daughter isotope. If we have lots and lots of parent and very little daughter isotope, then we know that it has to be very, very young. It hasn't even gone through one half-life yet. If we measure and we've got about 50% parent and 50% daughter, then it's gone through about one half-life. If we measure and we've got lots and lots of parent and very little daughter isotope, I've got that backwards. If we measure and there's lots and lots of daughter and very little parent isotope, then that means that it's gone through not just one, but many half-lives, and therefore the sample is old. This is the general idea of radiometric dating. Now, different systems, parent-daughter systems, have different half-lives. For example, carbon-14. If you've ever heard of carbon dating, this is one type of radiometric dating. It's often used in archaeology and anthropology. So in this case, we have carbon-14 turning into nitrogen-14 with a half-life of around 5,730 years. Well, because of how long this half-life is, that means that it's going to be effective from about 100 years out to about 70,000 years. After 70,000 years, there's so little parent isotope remaining, we can't really tell anything anymore, other than it's older than about 70,000 years old. Okay, so these ages are not good to help us figure out the age of the solar system, but it works out very nicely to figure out human civilization. Hey, this is the time span of human civilization, which is why we use it in archaeology and anthropology. Well, other systems have much longer half-lives. For example, potassium-40 turning into argon-40 has a half-life of 1.3 billion years. Uranium-238 to lead-206 has a half-life of 4.5 billion years. And rubidium-87 to strontium-87 has a half-life of 47 billion years. So what we've done is we've collected the very oldest Earth rocks, the oldest meteorites that have landed on the Earth, and moon rock from the Apollo moon missions, as well as some follow-up sample return missions, and used radiometric dating. And the very oldest samples all seem to agree that the solar system formed about 4.56 billion years ago. This is a number that you should probably remember. The solar system is about 4.5 billion years old. All right, here's another question. A sample of material shows it has very little daughter isotope compared to the parent isotope. If it has very little daughter and a lot of parent, then the sample is A, very old, B, has gone through only one half-life, C, has gone through several half-lives, or D, is very young. Go ahead and think about it, and we'll discuss in just a bit. What do you think? So we know it has a very little amount of daughter, but lots and lots of parent. That means that it hasn't even gone through one half-life yet. It hasn't had much time to decay. So in that case, it's going to have to be D, very young. I hope that makes sense.